In this video, we're going to talk about quadratic functions. So in the previous video, we talked about linear functions, and it's that special kind of class of functions that talk about straight lines, non-vertical lines. In this, we're going to have another special class of functions that we'll refer to as quadratic functions. Sometimes they're called parabolic functions, and we'll see why here in a little bit. So anyway, a quadratic function is one that can be written in the form f of x equals ax squared plus bx plus c. Our a, our b, and our c here will all be real numbers. Now, it's possible that the b could be 0, it's possible the c could be 0, but in order to be a quadratic function, the a has to be not equal to 0. All right, so the most straightforward quadratic function that we have is f of x equals x squared. And we can get a graph of this function by choosing some values for x, plugging those in for the function, plotting the dots, and then connect the dots. So let's do that. Let's just pick some values for x, plug them in, and get values for y, or for f of x in this case. Putting the -3, -2, -1, 0, 1, 2, and 3 into f of x. Remember, f of x is just take the x value and square it. We square all these, we get these values here. Pretty straightforward. Now we'll just use these to plot points and connect the dots. Okay, so here's your -3, 9. Here is your -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. So those are just plotting the points and connect the dots. So we get this U-shaped piece. Here's the x-axis down here at the bottom. So this is everything here is above the x-axis. Every quadratic function that we run across will have this same basic U shape. It may be flatter, it may be skinnier, it may be upside down, and it may be moved around, but every quadratic function has that same basic shape, and that shape in this case is what's referred to as a parabola. Okay, so one key characteristic that we're going to take advantage of is the fact that it has that one point where it turns around. Let me go back here. I'm talking about this point here, right? The function was going downward, it hit the origin, and then it turned around and went back up again. And every single parabola is going to have that point where it either bottoms out and goes back up or tops out and goes back down. That turning point is what we refer to as the vertex of the parabola. And we're going to spend some time talking about how do we find the coordinates of that vertex for an arbitrary parabola. Another characteristic that we have is what's referred to as symmetry. Let's go back again to the graph of that parabola. Pardon my backing up. What I mean by symmetry here is if we take this vertical line that goes straight down and goes through the vertex, then this is a mirror, the left-hand side is a mirror image of the right-hand side across that line. We can think of that line as a mirror. Okay, so go back over here. We always have symmetry around that vertical line, and we refer to that vertical line as the axis of symmetry for the parabola. All right, so I mentioned that we're going to be interested in figuring out what the coordinates of the vertex are for some arbitrary parabola, especially for application problems. To that end, we're going to need to be able to put the parabola in what's referred to as standard form. And we'll talk about how we do that in a little bit. But the standard form of a quadratic function is this one. So the a here is the same a that we used for the ax squared at the beginning. We have x minus h quantity squared, and then plus k. And again, here all the h, a, and k are all real numbers, and a has to be not 0. All right, so we're going to investigate what happens with each of these numbers for the graph of a parabola. So I'm over here using the graphing calculator at desmos.com. This is a free graphing calculator app that's very, very useful because you can type in functions, you can evaluate functions, you can do all sorts of manipulation with functions on this app. It's a great graphing calculator app. I'm using in this case to use what are known as sliders. All right, so here is my function in standard form, a times x minus h quantity squared plus k. And again, like I mentioned before, we're going to investigate what happens as we change the a, the h, and the k. Let's first change the h. So notice here where I've got this defaulted, I've got the a starts at 1, h starts at 0, k starts at 0. I've got the function f of x equals x squared. That's the one we graphed earlier. Let's see what happens if I move this h around. Make it positive, make it negative. So I'm just going to grab it and slide it. I'm going to make it more positive. Notice that we're sliding over to the right here. H is 1. We've slid the parabola over to the right 1. Make it 2. I've slid it over 2 units. 3 units. 4 units. So notice as my h is getting positive, more positive, notice the formula is x minus h. You gotta be careful with that. As h gets more and more positive, or this is x minus a bigger and bigger number, we're going farther to the right. Let's move it to the left. Here's negative 1, negative 2, negative 3, negative 4. And notice again here, when those h's are negative, or we had x plus 4 squared, for example, that would be 4 units to the left. So that as this h changes, the parabola goes left and right. Let me reset this back to 0. Let's see what happens as we change the k. Now remember, when the h was positive, it moved to the right. When the h was negative, it moved to the left. But remember, we're doing a minus h here. Okay? On the outside, we got a plus k. But notice again, if I make my k positive, we're going up in this case. Notice that's 1 unit up, 2 units up, 3 units up, and so on. We go to the left. We know if we subtract, 1 unit down, 2 units down, 3 units down. So as we subtract k's here, it's going down. As we add k's, it goes up. Okay. So notice it seems a little bit backward, right? Because this would really be subtracting h's. It's going to the right, going in the positive direction. Okay. Be careful with that. All right, let's see what the a does. We move these back to 0 again, just to keep things simple. Make the a bigger. Ooh, it gets narrower. There's 2, there's 3, there's 4, there's 5. It's really making it narrower. It's getting a vertical, what we refer to as a vertical stretch. It's making it 5 times as tall. Okay, we're multiplying all those original y coordinates by 5 each time. Make them smaller than 1 in this case. Here is 0.8, 0.7, 0.6, 0.5, 0.4, 0.2, 0.1, making it really flat, right? So as those numbers are between 0 and 1, we're doing a vertical compression, or making it flatter. What happens is when this gets to negative now? Well, notice as soon as it flips to negative, we're upside down now, right? It's going downward. So that negative sign reflects the graph of the parabola across the x-axis. We refer to that as opening down. So here, when it's positive, when that a value is positive, the parabola is opening upward. That's what we refer to that as. If we make it negative, it's opening downward. Okay, so that's what the negative sign tells us. Notice again, though, if I ignore the negative sign and make the a's bigger, notice that graph is getting narrower and narrower. Making the a smaller makes it get flatter and flatter, just like it did before. So that's the different effect that each of those has on the graph of the parabola. So let's see if we can summarize that. All right, so when we have this in standard form, when I have x minus h, quantity squared, and plus a k, the vertex is hk. So again, make sure you pay attention to that's basically the opposite signs, right? The axis of symmetry, remember that's the vertical line that goes right through the vertex. So the axis of symmetry will be x equals h. And then if the parabola opens up, if the a is greater than 0, the parabola opens down if the a is less than 0. And remember that the bigger the a gets, ignoring the negative sign, so looking at the absolute value, the bigger the a gets, the skinnier the graph gets. All right, so we mentioned that the vertex is a turning point. When the parabola opens upward, the vertex is the lowest point of the graph. We refer to that as the minimum of the function. When the parabola opens downward, the vertex is now the highest point of the graph, and we refer to that as the maximum of the function. And there will be application problems where we'll be interested in finding either the maximum or the minimum of a function. So let's do an example here. Let's find the vertex, axis of symmetry, and x-intercepts of this function. F of x is equal to negative 2x squared minus 8x plus 10, and then let's graph it. All right, this is quadratic, certainly, because we've got x squared, and this term is negative. The a here is not 0, it's a negative 2. Okay, so it'll certainly be a parabola, and also since the a is negative 2, which means that the a is less than 0, this parabola will open downward. In order to be able to write down what the vertex and the axis of symmetry are, we need to have this function in standard form. To be able to do this, we need to do a technique called completing the square. All right, so let's see how we complete the square. Here's our function. The first thing we want to do, notice that the a is factored out in front here, right? So that's the first thing we're going to do, is we're going to factor off that coefficient that's in front. Now notice that I only factored it off of the x squared and the minus 8x piece, because that's the piece that we want to complete the square on, this piece here. The plus k on the end is what's going to tell us the y coordinate of our vertex. So I don't need to worry about having the 10 on the inside. I just need to factor off the coefficient off the x squared and the 8x. So factoring out the negative 2 here, we're left with x squared plus 4x. Here's how you complete the square. I want to be able to factor this expression as a perfect binomial square. In order to do that, you take the coefficient that's on the x, which in this case is a 4. You divide that in half. 4 divided by 2 is 2. And then you square it. 2 squared is 4. So that's where this plus 4 is coming from. Again, half the coefficient and square it. Okay. Now, we can't just magically add a plus 4 in and keep everything equal, right? Everything here has to stay equal. All right, so that's where this plus 8 comes in. Let's see where that's coming from. Plus 4 is on the inside of these parentheses. So that means this plus 4 is really being multiplied by this negative 2. So we haven't really added 4. We've really subtracted 8, because we've added a plus 4 times a negative 2. Since we've really subtracted 8, we've got to add 8 to keep everything equal. Now we can factor. We've rigged it so it factors every single time. This will always factor as x, whatever the sign is, half that coefficient, and then quantity squared. This factors as x plus 2 squared. We've rigged it so it does every single time. That's what completing the square does. All right, so now we have it in standard form. We recognize that the vertex of the parabola, this is x minus a minus 2. Remember, the standard form is x minus h quantity squared. So the x coordinate is negative 2. The plus k piece is the plus 18. So the vertex is negative 2 comma 18. And the axis of symmetry then is x equals negative 2. The problem also asks us to find the x-intercepts. To find x-intercepts, we need to solve the equation f of x equals 0, set it equal to 0, and factor in this case. So in this case, I will factor out the negative 2 because I really do want to factor this since it's set equal to 0. X squared plus 4x minus 5 factors as x plus 5 times x minus 1. That tells me that x could be negative 5 or x could be 1. That's the two solutions to that equation. Hence, the x-intercepts are negative 5, 0, and 1, 0. We now have enough information for a graph. The vertex was the point negative 2, 18, so that's plotted way up here. Our x-intercepts were negative 5, 0, and 1, 0. Put those on the x-axis, make a nice curve, if you will. Connect the dots and make a nice curve. Also, we could have found the y-intercept, and we see that here. Y-intercept would be found by putting 0 in for x. When you put 0 in for x, you get 10 out, so the point 0, 10 should be on there, which it is. All right, let's see if we can do an example problem. An application problem. Two numbers have a sum of 20. We want to find x and y so that their product is as big as possible and find the maximum value. All right, so we're told that x plus y has to be 20. We're told that the sum of x and y is 20. And that means that if we solve one for the other, let's just solve for y in terms of x, we get y equals 20 minus x. The problem is asking us for the maximum product, the maximum of x times y. Okay, well we know that from what we talked about with quadratic functions, we want to find the vertex, but we want a quadratic function with one variable. This has two. That's why we solve for this expression of y in terms of the x. We can plug in 20 minus x for the y, and then simplify, and we get negative x squared plus 20x. This is now a quadratic function. If we find its vertex, since it opens downward, it has a negative a value. Since it opens downward, the vertex will give us the maximum. Okay? And that's exactly what we're being asked to find. So we'll do the same process that we did in the previous problem. We're going to put this quadratic function into standard form. We're going to factor off the coefficient on the x squared. We're going to complete the square. All right, this coefficient is 20. Half of 20 is 10. 10 squared is 100. So we're going to add 100 in here. But notice we're adding the 100 inside the parentheses. Outside the parenthesis is a negative, right? So really we're not adding 100, we are subtracting 100. So to keep everything equal, we're going to add 100 on the outside. Now we factor. Remember, we've rigged it so this factors the same way every single time. It's always x, same sign, half that coefficient, quantity squared. Now we can read the vertex of the parabola. It's 10, because remember the standard form is x minus h, so it's 10, 100. That means that our x equals to 10 is one of our numbers that we're looking for, because that's the x coordinate. We can figure out the y by plugging that x value into the relationship that we found between x and y, which means our y is also 10. The maximum product now is 100, and we can determine that in a couple of ways. One way is it's the y coordinate of the vertex, or we could literally just multiply the two numbers together to get 100. We found one number was 10, the other is 10, the product is 100. So there's a couple of ways to get that particular maximum value.